session. Today, the first speaker of the afternoon session is Professor Masahiro Hotta from Tohoku University in Japan, and he's going to talk about expanding edges of quantum Hall systems in a cosmology language. Masahiro, it's a pleasure to have you. Whenever you want, the floor is yours.
Thank you. I'd like to thank the organizers, all of the organizers, to invite me this night meeting. This talk is based on a paper in collaboration with Yasuda Nambu, Yuki Sugiyama, Kazuhiro Yamamoto, and Go Yusa. Okay, let's move the introductory part. As you know, we only have our single universe, so it is difficult to collect statistics for the early era of the universe. This is a very serious obstacle to answer the big question. How did our universe develop from its earliest moments? And here we have a note. The observation of Hawking radiation out of black holes are also quite difficult. But Bill Unruh first proposed a simulator of a black hole and its Hawking radiation using sound waves in a transonic fluid flow. And in this RQN, we have many other gravity analog talk. I'm sorry if I forgot to write some speaker's name about the gravity model, and then I'm sorry. Okay, so our target is the following: to create creating 1+1 dimensional universe simulators using quantum Hall edge currents. So this experiment is just funded, and the experiment just started by the group at Tohoku University. The universe simulators can explore the spacetime dimension-independent conceptual cosmological issues, including trans-Planckian problems of Hawking radiation and inflation universe. And also we can explore quantum classical transition of the field fluctuation in early universe. And finally, we can detect entanglement structure in early universe by using this simulator. So what is trans-Planckian problem? Let me briefly explain. So first of all, let's consider the gravitational collapse of star, which generates a black hole. This is the event horizon, and here we have a singularity. And this black hole emits Hawking particle. The wavelength of the mode function for the particle is typically order of black hole radius size. However, the wavelength of the same mode of the particle is very, very small compared to Planck length near horizon. Okay, then a precise description of the mode in the path regime is required for fundamental microscopic theories, such as loop gravity and string theory. It is possible that Hawking's approximation is incorrect, has a serious discrepancy. However, his results appear to be correct. In reality, the formula for Hawking temperature and the black hole entropy with the horizon area are consistent with the theoretical result of general thermodynamics and also statistical mechanics with state counting in string theory. Thus, why Hawking's analysis works so well despite being semi-classical is a mystery. This is called the trans-Planckian problem. And also, in the inflationary universe, the Hawking radiation come out of the cosmological horizon. This is a very similar situation of the black hole. The temperature of Hawking radiation is just half parameter over 2 pi. Then So we have another trans-Planckian problem in this situation. If Hawking's prediction is correct, analog inflation universes also emit Hawking radiation, no matter what the analogs are made of. Quantum Hall analog horizons possess the magnetic length as a cutoff mimicking the Planck length. This phenomenon poses a quantum Hall analog version of the trans-Planckian problem. And so we can explore this problem by using the quantum Hall system. And also, we can explore the quantum cluster transition problem. The accelerated expansion in the inflationary universe provides a quantum field fluctuation that becomes classical fluctuation over the half-horizon scale. However, the relation has not been deeply understood between the existence of horizon and the quantum classical transition, especially from the viewpoint of quantum entanglement. However, it is possible to explore this problem by using this simulator. And also, our simulator can detect the entanglement structure in our universe. About the entanglement structure, we have many issues in the inflationary universe. For example, we have a Bekenstein-Hawking entropy for cosmological horizon, but very crucial question is the following. So this entropy can be interpreted as an entropy, or it is related to the Newtonian formula, or emergence of spacetime from quantum information can be possible or not. It is usually called it from qubit. However, in experiment, by performing this experiment, the entanglement may be directly detected. So we can verify the conjecture or theories, many interesting features of the string theory or quantum field theory and GR. So in this sense, this quantum universe simulator is very interesting. And here we have a very question of. So quantum energy teleportation experiments are possible by using quantum Hall edge. The QET is just a zero-point energy physics of the quantum systems and very interesting. But this year, we have a big news from Edward. So this March, an experimental result of a finite temperature version of QET has been reported using nuclear magnetic resonance. So this experiment are based on my theoretical two papers. And I think this is a very crucial experiment and a very amazing achievement, I think. But our quantum Hall experiment will verify the vacuum state of QET at zero temperature and directly measure the teleported energy. This is an interesting point for the quantum Hall system. Okay, so this is today's plan of my talk. The first, I would already provide an introductory part. And in section 2, I will briefly review about the quantum Hall system. In the third part, I'd like to mention about our new result for expanding quantum Hall edge. After that, I would like to summarize my result and this talk. And let's move to the quantum Hall system. This is the quantum Hall system, and this provides a famous effect called as an integer quantum Hall effect or fractional quantum Hall effect. And by using this edge state, we can construct a quantum universe simulator. So here we have H current, which the edge is now conductive, even though the bulk is insulating. The skipping cyclotron orbits can be viewed as a quasi one-dimensional channel. Such an edge channel behaves like a chiral Rattinger liquid, along which current flows unidirectionally. So this phenomenon can be described by a chiral mass field in one dimension, that is the CFT, conformal field theory. And then the chiral field operator, in terms of density operator, is denoted by law of X. Then, so we can compute the commutation relation. And we get this relation that here nu is the filling factor of the system. And by using the commutation relation, the Hamiltonian, we can get a dispersion relation like that. So this shows that the gapless mode or the edge state. By using this edge, we can consider a quantum field, a chiral boson field. And at the ground state in low temperature, we have also zero-point fluctuation of electric potential at the surface. And delta B can be measured directly in our experiments. Okay, let's move to the third part. Okay, so let's focus on the edge state and create an expanding universe simulator. Okay? If this one-dimensional edge can be controlled dynamically, the edge may be described by 1 plus one-dimensional CFT. This is just a toy model of the universe. So if the edge is stationary, this describes a flat spacetime. But if the edge has an expanding region like that, so this corresponds to a curved spacetime. By changing the confinement potential in time with injection of additional electrons to the surface, the edge is expanded. And then we can talk about this expanding edge in a cosmology language. So this is our result. So any expanding edge corresponds to an expanding universe in our 1 plus one-dimensional dilaton-gravity models. For the detail, please see our paper. So the main result is following. Okay, so now we fix the time schedule of the expansion of edge, which is described with this factor. Then we can find the 1 plus one-dimensional dilaton-gravity, the which action is given by this equation. This large phi is correspond to a dilaton field, a real scalar field, which is named the dilaton field. And the B of phi is a self-interaction term of the dilaton field. And also, if you give some action of the dilaton gravity like that, then so our experiment realizes such an expansion of which corresponds to the solution of this theory. So in this sense, the H current is our universe simulator. For example, when we consider V of phi equal minus phi, and this model becomes Jackiw-Teitelboim model. So this model has an aided spacetime as a solution. The metric is given by this. The H is given by just √2 and lambda. And the scale factor is computed like that, and the dilaton field time evolves like that. And then we simultaneously obtain another model by changing the this parameter H into an IH, pure imaginary parameter. Then this model converted into a digitalized model. the potential term is now just phi. And then the equation motion has a solution of digital space. This is scalar curvature and dilaton field evolves like that.
Masahiro, 5 minutes.
Yes, five minutes. Okay. So the expanding region 2.
Sorry, no, my bad. You still have 9 minutes.
9 minutes, okay. So expanding region 2, we have such a space-time metric. And by introducing another coordinate x and introducing a right coordinate like that, then the space-time metric is given by this equation. And also, we can introduce another conformally flat coordinate x in. And x in can be spanned in simultaneously in region 1 and region 2. Okay, region 1 is a flat spacetime. Its metric is given by this equation. And region 2, the metric is given by this equation in terms of x in coordinate. Similarly, region 2 and region 3, we have another conformally flat coordinate system, x out. And region 3 is also a flat spacetime. And region 2 can have such a metric form in terms of x out. And also we can connect the two regions at this boundary, x minus L over 2, smoothly. Then, so the function of the coordinate change is completely fixed. So, in this sense, x in is a function of x out. So this function can be fixed using the two coordinate system in the region 2. So this is our main result. So first of all, we define f out of x by using this equation. And after computing the f out of x, we can compute f of x by using this formula. For example, in the Jackiw-Teitelboim model, we can get the explicit form of each function like that. And this function for the Dojita case represent the existence of a cosmological horizon. Here, we have two typical features in the plot of f of x. The domain of the range of f of x becomes self-indefinite, which indicates existence of horizons in the present spacetime. And this is a Penrose diagram of expanding quantum Fourier. And here, the shade region is just connected region 1 and region 3. And also, it is very interestingly, this expanded edge represents a 1 plus 1 dimensional version of Einstein-Rosen bridge in digital space and two flat spacetime. If we take a small value of L, then we have a traversable bridges between region 1 and region 3. But if we take a large L, then so this bridge becomes untraversable. So by changing such a parameter, we can perform experiment such interesting spacetimes. Now we consider master scale field as the edge. Then also we consider an input wave in the region 1. And this propagates region 2 and reach region 3. Then we can predict the output waveform by using this formula. And so this is just an example of the waveform, output waveform. The input waveform is just a plane wave, but the output waveform is given by this plot. And here we have a very severe oscillation as the initial phase. And in the later phase, we have a very flat behavior of the plot. So these plots, this behavior corresponds to the existence of the cosmological horizon. And also here we have, we can consider analog trans-Planckian region. So we can explore the trans-Planckian problems by using this behavior.
Now it's 5 minutes for real. Sorry.
Okay. So by using this mode function, we can compute the Bogoliubov coefficient and the particle creation expectation value, especially. And then, so we can notice that that is the standard Planckian form, and we can read out the temperature, and the temperature is just a Hubble per meter over 2 pi. This is just the correct value of the Hawking temperature in the influential universe, which can be observed in the region 3. Okay. Then, before closing my talk, I'd like to make some comments. So this quantum system, this quantum Hall system, very interesting because the edge fluctuation as quantum matter in 1+1 dimensional classical spacetime is described the quantum superposition of the field configuration in a fixed background spacetime, which can be computed by using such a path integral. But very interestingly, there is a possibility that the same quantum Hall edge can be also described by the quantum gravity theories. So, so now the quantum fluctuation of the edge corresponds to the quantum fluctuation of the spacetime itself in 1+1 dimensions. In this sense, we have a superposition of quantum spaces in this system. Then, so the crucial question is the following. What kind of quantum gravity theory, or what, so is it possible to describe by dilaton-gravity like JT model also? So this can be verified, or this can explore, this can be explored by our experiments. Okay, this may be interesting. And also, there is a possibility to explore the island conjecture experimentally using this quantum Hall edge in the multi-layer. This is another comment. Okay, so let me summarize my talk. We have started creating quantum universe simulators made of quantum Hall edges. Conceptual cosmological issues, including Hawking radiation, trans-Planckian problem, and the quantum classical transition of field fluctuation, can be studied in the experiment. The expanding edge current will be explored to open a new window quantum Hall physics, quantum Hall system physics. Thank you very much.
Thank you very much, Masahiro. Thank you for talking.
Yeah. Thank you.
All right, there is time for one question. Remember that there will also be questions at the end of the session.
Okay.
Cisco, yes, go ahead. You can unmute yourself.
Hi, thank you very much for the talk.
How are you? yeah, how are you?
I'm good.
Okay.
I know we're stuck on time, so I'm going to get right to the point. I have two very quick questions. They're related.
Okay.
How much freedom do you have experimentally to dynamically change what the cosmology is doing in region 2?
Sorry, so your voice.
Do you have much freedom of that, or is it kind of just okay? Sorry.
Okay, so
I will slow down.
So we have instability of internet.
How much control? What's that?
We have instability of internet. So your voice is broken.
Okay.
Yeah.
Pardon me. In region 2, how much control do you have experimentally to create a dynamical space-time cosmology, to change the cosmology?
That's a good question.
Is it fixed,
Yeah,
or
that's
is
a
it?
good question. So my collaborator, experimentalist, user, now trying to control by changing the confinement electrical potential, and also they injected the additional electrons. So in order to keep the filling factor itself. So essentially, these two conditions are required for such an experiment. So now we have edge. Edge is generated by such a confinement potential. Then we change the confinement potential. Then so edge expanded. But we need to add the electron in order to fix the filling factor of the system itself. This is the main concept of this experiment.
Yeah. Cool. Okay.
All right. Thank you very much for the question.
Thank
Any other
you.
questions? Time for one more.
Thank you, Masahiro.
All right. Well, if there aren't any more questions, remember still that we have Slack, and also we have questions at the end of the session as well. Let's thank Masahiro again for your talk. Thank you very much, Masahiro.
Thank you very much. Thank you.